So there's this buzzword that's been flying around all over the place and kind of catching up steam throughout the development community, and it's WebRTC. But what exactly is WebRTC? How does it work? And why would we use it? We'll answer all those questions and more in this video. So the RTC in WebRTC stands for real-time communication. This means basically connecting and communicating with people like right away. This can be used for a lot of things like video calls, audio calls, maybe messages. But before we get too deep into WebRTC, I want to go over WebSockets because I think differentiating the two and knowing which one to use when is an important thing to understand. So the WebSocket you could think of as a real-time connection to some sort of data, maybe in a server or something like that. So let's say you wanted to get the stock prices of a specific sort of stock from some sort of exchange. So normally you'd do a request and get a response that tells you it's $41 right now. But for normal request and response, the client device is the one that has to first send out that request in order to get any information back. When you create a WebSocket, you basically ask the server to update you anytime the data inside of it changes. So at first you get that $41 request back, but then let's say we're being realistic about stocks and they usually just go right down. And inside that server, the data piece gets updated to being only $10 now. Will get updated with the response saying that it's $10 now, and the stock price here will get updated $10. And technically that line I drew wouldn't have been drawn at that point in time. It would only be drawn once you get that response back from the server. So this is great, this works. But with WebSockets, you get a little bit of a delay. So if we think of this as the database server, there's another server that actually is getting that specific data from wherever they get stock data from. I don't even know. But this is the thing that will be first updating the price here. And then this WebSocket would be the actual one sending out the update to whatever device is using it. So this type of solution works really well for data transfers. Anything like that stock app, like text messages, emails, anything like that. A 1 second delay does not matter for most people. But there are very specific cases where this type of delay is kind of unacceptable. The most straightforward one is video and audio. Imagine if you were having a video call with someone, you'd have up to maybe 1 second of delay between talking and seeing the other person. That'd be kind of a mess. In this case, a direct connection from here to the phone would be the optimal thing to do. Maybe a better example that helps explain this, and ignore my ugly little Twitter bird. This is supposed to be a Twitter. So normally, let's say you're using Twitter. If you're writing out a tweet, that's kind of data that doesn't really matter. So it makes sense to pass to the database, which then updates the other phone with your specific tweet. But now let's say you go on a video call using whatever service you want to use. If you were to send that video, If you were to send that video call first to the database and then to this device, that'd be kind of a mess. And that's where WebRTC comes into the picture and kind of saves the day. So WebRTC is actually an API that was released by Google in 2011. The nice thing is they released it as an open source project, so anybody can go and contribute to it and kind of figure out any potential leaks or errors that could happen using WebRTC. So now that we know that WebRTC is faster and more efficient, why would we not use it for everything? Well, the very first reason, it's nice to have a central hub if you have data. So for example, tweets, it doesn't make sense to everybody share tweets between each other. It makes sense to have a central hub. But a second point is that WebRTC runs on UDP. UDP is one of the reasons that WebRTC is actually so fast. But the problem with UDP is it has no acknowledgement of receiving the actual information. So whenever you're using WebRTC, you basically just spit out data and you don't care if the actual user got it or not. There's this protocol called TCP that actually does that type of acknowledgement, but WebRTC doesn't use it as of now, so we're not going to get any more deeper into that. So the next question you might have is, if UDP doesn't give you any acknowledgement that the message was received or that the data was received, why would you use it? Well, for video and audio, we don't really care if we miss a couple bytes here and there. If you're missing one frame in a video call out of however many frames per second you are retrieving it at, if there's a little bit blip in the audio, nobody's really going to even notice. So there are specific cases where WebRTC really makes sense. In other cases, you might as well just use WebSockets. But how does a WebRTC session actually work? So let's say we have these two phones, phone 1 and phone 2, that want to start a video call together. They decided they will be using WebRTC for this. So how does the process actually start? Well, phone number 1 has to send out an offer basically saying, this is my information. I want to create a call with these settings. This offer will be an SDP. That stands for Session Description Protocol. We'll go into that a little bit deeper after this. So phone number 2 checks, sees that all that stuff works for him. They accept the offer. And they respond back with an answer, which is also an SDP. And phone number 1 accepts that answer, and you have an active WebRTC session. So this SDP is a very important part of the WebRTC workflow. Like I said, it stands for Session Description Protocol. You can think about this as just kind of like a string of characters or list of stuff that gives you information about the specific call. It'll have things like the codec, whether it's video, audio, or both, something called ICE candidates, which we will get into a little bit later, and a bunch of other stuff that just basically describes what kind of call this is going to be. By the way, for this, we send the SDP through a server, but this could be sent through anything. You could send it through a text message to someone. It doesn't really matter how it gets to that second device, as long as it gets to that second device. So what the heck is this ICE candidate? You can think of it as just available IPs for each device to connect to. IPs are like addresses of the specific device. So if we go back to this graph over here, let's say this device or computer has an address of 1.1.1.1. This one has a 2.2.2.2. Now, Now there are some devices where their IP address is public for everybody to know. So let's say that's one of the cases here. We would just put that IP address into the SDP and you wouldn't have to worry about ICE candidates or anything like that. But for most cases, your IP address is not something that's publicly shared. Let me redraw this portion of the diagram down here. So the reason it gets a little bit more difficult is because of a NAT, which stands for Network Address Translation. So basically, whenever you send something out of your device, your computer, your phone, whatever, that address of that specific device gets hidden from the rest of the internet. The offer and the answer goes out to the ISP and comes back from the ISP. If you're interested in how routers and ISPs and stuff like that work, I have a video in the description, probably a little pop-up here too, where I covered what the internet actually is. And we go into detail about these specific things. But in general, the router is something that like routes your piece of data out to where it needs to go on the internet. And the ISP is the cable that you have inside your house that provides the internet to your specific house. So the way the NAT works, again, we have this device 1.1.1.1 trying to communicate with this device 2.2.2.2. You want this one to communicate with 2.2.2.2. We send the message to the router. The router then creates something called a NAT table. So you could pretty much think of a little database that says from and to. So we're going from 1.1.1.1 to 2.2.2.2. So that public IP then gets hidden by the router. So you're no longer sending it from 1.1.1.1. You're sending it from 5.5.5.5. That message goes out over the internet. When you receive the answer will be from 2.2.2.2 intended for 5.5.5.5. This then checks the table. In the table, you see that you were looking for a message from this specific IP address. So you're like, okay, I got something from this. I need to route it to this specific device. So that then gets converted. And we receive a message from 2.2.2.2 to 1.1.1.1. And that device has all the information it needs. So that's what a NAT is. But there are 4 different types of NATs. This is just an oversimplified idea where it only looks for this type of stuff. There's a couple other checks and balances that a NAT does, but the general idea is the same, and we're not going to get into each of the 4 types, but just know that there's 4 types. So now how does all this NAT stuff happen? It happens through a stun server. So remember, for WebRTC, you need to provide a specific IP. So you need an IP that works with the NAT. To get this IP, you need to spin up what is called a stun server. So stun server stands for Session Traversal Utilities for NAT. This is just a server that basically gives you public IP addresses that you can put within your SDP to send to the other person. So if we go back to this graph up here, instead of putting that 1.1.1.1 into the SDP, this device will reach out to a stun server, which will return IPs to it. And then those IPs will get put into the SDP. And if you remember, this candidates was a plural. So a stun server can give you back multiple IPs. It will probably even include this IP just in case it's publicly facing. But the main idea, you're giving your IPs to the SDP to send over to the other device so that they know where and how to connect. So if you start learning more about WebRTC, you'll hear about turn servers as well. So usually they're referred to as stun and turn servers. The turn part stands for traversal using relay around NAT. So remember, there were 4 types of NATs. So a symmetric NAT is one of the more complicated types of NATs to get over, but we don't really need to get into that. It's the same concept, just more complicated. Last little extra piece I wanted to add in is this SDP. We're putting all the ICE candidates at the beginning. But there's a technique that's very commonly used called Trickling ICE candidates. So since it takes some time for this server part to actually execute, you first send out your SDP. And then as you retrieve the IPs, you send them out one by one to the SDP, and it slowly collects all of them. And then once it finds something that hits, you can connect usually faster than you would just by waiting for all of them. Now, how did I get interested in this WebRTC? Well, if you've been watching my videos, you probably know that I work for a company called Agora. So at Agora, we provide video, audio, and data synchronization, as well as other tools to help people create real-time communication apps. Now, why would you use Agora versus just using raw WebRTC? Well, first, Agora simplifies the process a lot. You don't need to know anything about offers, stun and turn servers, SDPs, ICE candidates, none of that. We actually have like ready to go solutions where you can do it in like 3 lines of code. But the coolest part, the part that interests me the most, is that even though WebRTC is very efficient and more efficient than Websockets, it can still be a lot faster. So in the previous video, we kind of went over how the internet actually works. And the internet is just a bunch of routers everywhere. So these routers will try to find the most efficient way for you to connect using WebRTC. So maybe this is the most efficient way. Now that's great, but one thing to remember is this whole infrastructure and ecosystem was not built for WebRTC. It was built to manage lots and lots of data flow to lots and lots of other people. But since Agora's whole business and everything has been built to support real-time engagement and real-time communication, this network has been made to be as efficient as possible, using the most efficient routers to make sure that your video calls, audio calls, or even just data synchronization is as low latency and as fast as possible. But that's WebRTC. This technology is super interesting. This topic interweaves a lot with the internet video that I created. So if you want to learn kind of the basics of all this type of stuff, there's a video that should be popping up right now called How the Internet Works. So I definitely recommend you click on that. But anyways, thank you for watching and see you next time.